Good morning. In this video, we will talk about how to calculate the equilibrium constant. In our learning guides, this lesson covers LG 3.5 to LG 3.6.4. By the end of this lesson, the students are expected to be able to achieve the following target outcomes. 1. Calculate equilibrium constants of reactions that result from reversing another reaction, multiplying another reaction by a certain factor, and or combining two or more equations with known KEQ values, as in a multi-step reaction. Manipulating the balanced chemical equation in any way will change the equilibrium constant expression and thus the equilibrium constant value. For today, we will tackle three such manipulations. The first being reversing a reaction, in which case the new equilibrium constant value is equal to the reciprocal of the original K value. When we multiply a reaction by a certain value n, the new value of the equilibrium constant is equal to the original value raised to the exponent n. And finally, when we sum up two or more reactions, the new equilibrium constant value is equal to the product of the individual equilibrium constants of each reactions being summed up. Let us now tackle a sample problem. If K is equal to 3.8 times 10 to the power of 4, for the reaction N2 plus 3H2 producing 2NH3, calculate the equilibrium constant when we apply the following manipulation. First off, we have 2NH3 producing N2 and 3H2 gas. Looking carefully at this balanced chemical equation in number 1, and comparing it to the original equation, we see that number 1 is actually the reverse of the original equation. From the previous slide, we learned that when we reverse the original equation, the equilibrium constant value will be affected so that the new equilibrium constant value K, which we shall call as K prime, is now equal to the reciprocal of the original value. So computing now 1 over 3.8 times 10 to the power of 4, we now get K prime, the new value of the equilibrium constant, to be equal to the following. K prime is equal to 2.63 times 10 to the power of negative 5. In number 2, we have this new equation, 1/2 N2 gas plus 3/2 of the hydrogen gas producing NH3 gas. Now comparing this new equation to the original equation, we note that in the new equation, the coefficients is just equal to the original multiplied by 1/2. For instance, for N2, its original coefficient is 1 times 1/2 giving you 1/2. For H2, its coefficient is originally 3 times 1/2 gives you 3/2. And for NH3, its original coefficient of 2 times 1/2 gives you 1. From the previous slide, we learned that when we multiply the original equation by any number n, the new equilibrium constant K prime is just equal to the original value raised to the value of n. In this case, n is the value in which we multiply the coefficients of the original equation. Now, since we've multiplied the original equation here by 1/2, so the exponent here must then be 1/2. Taking out our calculator, we find that k prime is equal to 1.9 times 10 to the power of 2. As an example of two reactions being added together, let us consider the following problem. We are asked to write the sum of these two reactions and from then calculate the value of K when the following reactions are added. The value of K, we take note, is 3.92 for the first reaction, while for the second reaction, K is equal to 3.3 times 10 to the power of 4. Let us sum up these two equations. First, looking at our carbon monoxide CO gas, we see that carbon monoxide CO is alone in the two equations. We don't see CO appearing at all in the second equation, so we copy CO as it is. Next, let's look at our H2. H2, we note, is present here in the first equation. We see it being part of our reactant as 3H2. While for our second reaction, if we look closely, H2 is also present, this time as a product. Since H2 is present as a reactant in one reaction and a product in the second reaction, the H2s here will cancel out. However, the cancelling out will not be complete since their coefficients are unequal. So to be able to find out how much H2 will be left after we cancel the H2, we simply subtract the larger value, that's 4H2, minus the smaller value, which is 3H2. Subtracting these, we get only 1H2 left. And since the larger value is located in the product side, that is to the right of the arrow, we then write this remaining H2 to the right of our reversible arrow. The H2 is already done. Let us now look at our CH4. CH4, if we look closely, is present as a reactant in the second reaction and is also a product in the first reaction. Therefore, these CH4s will cancel out, and since the CH4s here have the same coefficient, so these two will cancel out completely. And CH4 does not appear in the sum of the two reactions. Finally, we have H2S. Looking at the H2S, we see that H2S does not appear in the first reaction at all. So we simply copy the 2H2S as follows. Now let us look at the products of these two reactions. Starting off with the CS2. For the CS2, we note that there is no CS2 available in our first reaction. Therefore, we copy CS2 as it is. The same is also true with the water. There is no water available in our second reaction, so we copy the water as it is. And so we have below the sum of these two reactions. Having summed up these two reactions, we are now ready to calculate the value of the K after we have added these two reactions together. The new K, which we shall call as K prime, is just equal to the product of K1 and the K. In this case, K1 is 3.92, while K2 is equal to 3.3 times 10 to the power of 4. Getting our calculators now, we can compute the value of K prime. K prime is equal to 1.3 times 10 to the power of 5. To help you practice how to calculate the equilibrium constant, you are now asked to answer numbers 1 to 2 in the formative assessment. The formative assessment is to be answered individually. However, you can pair up with your classmates so that you can help each other out in answering, and you can discuss your various approaches in order to answer the numbers 1 and 2. To further guide you along, at the bottom half of the page of the formative assessment, you will see the answers to numbers 1 and 2. By way of review for our upcoming midterm exam, let us consider the following sample problem. The Haber process, whose K sub C value is equal to 3.8 times 10 to the power of 4, is represented by the equation nitrogen gas plus 3 of hydrogen gas producing 2 of ammonia gas. Suppose the following equilibrium concentrations were observed at 127 degrees Celsius. For ammonia, its equilibrium concentration is 31 millimole per liter, and for nitrogen, its equilibrium concentration is 850 millimole per liter. From these, we are asked to calculate the value of the concentration of H2 at equilibrium. To answer this one, we need to summarize the given information. In our problem, we take note of all of the given information. First, we are given the balanced chemical equation, which we have copied as one of our given values. We have the K sub C expression, or the K sub C value rather, and we have also the concentrations of NH3 and the N2 at equilibrium, which we have duly copied. Given all of these information, we are asked to calculate the equilibrium concentration of H2. Having summarized these, we are now ready to solve this problem. Note that we are given the value of K sub C. Since we are given this value, this tells us that we need to have our K sub C expression written down, and that is what we've done right here. K sub C then is equal to NH3 squared over N2 times H2 cubed. Now looking back at our given values, we take note that the SI prefix Mili stands for 10 raised to the power of negative 3, and that 1 mole per liter is just equivalent to 1 molar. Molar is represented by the unit capital M. From these, we are now ready to substitute the given values of K sub C and the equilibrium concentrations to our K sub C expression. This gives us the expression shown on the screen. Now, in order to solve for H2 cubed, we do cross multiplication. By this, we multiply both sides of this equation here by H2 cubed, and at the same time divide both sides by 3.8 times 10 to the power of 4. Doing so gives us this new expression here, and from which we are now ready to solve for H2 cubed. From our calculator, we've computed H2 cubed is equal to 2.98 times 10 to the power of negative 8. Now we are after the equilibrium concentration of H2. Now to be able to get this value, all we need to do then is to get the value of H2 cubed and get the cube root of this one. Now getting our calculator, we will get the value of the H2 at equilibrium, which we find to be equal to 3.1 times 10 to the negative 3. Now that we have learned how to calculate the concentrations of chemical species at equilibrium from the equilibrium constant, you are now asked to answer numbers 3 and 4 in the formative assessment. Answer this one with your pair, discuss how you were able to arrive with the answer, and try to help each other out. To guide you in your answers, the values for the answers in 3 and 4 are given at the bottom half of our page. To summarize what we have learned in today's lesson, here are the following main points that we have discussed in this video. The equilibrium constant for a reaction is the reciprocal of that for the reaction written in units. When the balance equation for a reaction is multiplied by a factor n, the equilibrium constant for the new reaction is the original k raised to the f power. Finally, the equilibrium constant for a net reaction is the product of the equilibrium constant of the individual steps.